That little device at the end of your telescope's image train, the Astro camera, is the heart of the entire system. The telescope gathers light, and your computer develops the information contained within that light. But in the end, it's the camera that does the actual collection. And we astrophotographers are typically working with extremely faint objects, so we require cameras with specifications that are more precise and demanding than those of ordinary photographers. So today, I'm going to go into what I look for when I'm buying an Astro camera. This video is going to focus on selecting cameras specifically for deep sky objects and deep field imaging. These are the most technically demanding and expensive cameras. If your only interest is imaging the sun, the moon, or the planets, you might want to look into a planetary camera. Those objects are much brighter, therefore the technical needs of planetary cameras are much less demanding. Ergo, those cameras are much less expensive. But if your goal is to shoot deep sky objects and deep field objects, or if your goal is to shoot extremely faint objects within the solar system, then you might want to watch this video. Because among other things, I'm going to talk about how to select a camera that can capture signals so faint, it could almost be said the signal doesn't exist at all, for it is certainly at the very limit of what our atmosphere will allow. In so much as possible, I'm going to attempt to avoid math and just explain things in plain English, which is something we don't too often get on channels about astrophotography. It's not that math isn't necessary, it's just that most persons in the world don't think mathematically. I remember back in my university days, in one of my probability and statistics classes, the professor was writing out a formula on the blackboard that purported to describe a form of group behavior. And when I asked him if he could explain what the formula meant, he looked at me puzzled and said, "Well, it's right there in front of you." At the time, we were discussing predicting animal group behavior, and I told him the formula is a description of the preponderance of one behavior over another, but it doesn't really explain what's actually happening in the mind of the animal. He didn't quite seem to get that. And as I've talked about in previous videos, due to my profession, I spend a lot of time thinking about how people think, because understanding intelligence is literally part of what I do. And to me, that moment just profoundly illustrated the difference between the way a visual thinker like myself understands the world in contrast to a mathematical thinker. And most people are not mathematical thinkers. Generally, we can use and understand math just fine, so long as we know what the variables mean. But when most people think about the world, they think about it visually, not in terms of mathematical formulae. So, recognizing that most people do not think in mathematical symbols, I'm going to try to explain everything in plain English, and just really bring all of this into a world that all of us can easily understand. This image is essentially a stats summary. For those of you who maybe played tabletop RPGs in your college days, this would be your character's stat sheet, but for your camera. And a lot of what you need to know in choosing a camera is right here. We're going to go over this from left to right going down. The sensor type is in the top left. This camera, the Player One Aries M, which is my personal favorite, has the Sony IMX533 sensor. This sensor is almost legendary for its extreme sensitivity to light and its ability to produce excellent astrophotography images. There are other good sensors out there, but whenever you buy a camera, the sensor really is the first thing you should look at, because the camera itself is just a chassis. The sensor is the heart of the camera. My suggestion would be to pop onto astrophotography sites and take a look at the camera sensors that are well reviewed. If thousands of your astrophotography peers are complaining about or loving one sensor or another, it's a good indication that you might want to avoid or buy that sensor. The category just right is the format, which refers to the sensor's size and shape. Camera makers will typically list the sensor shape as 1 inch, APS-C, full, or by a more specific measure, such as the sensor shape in millimeters. And often they'll list both. The Sony IMX533 is a square sensor, and there aren't too many of those, but to be honest, for astrophotography, I much prefer the square sensor. Because my sensor is square, I don't really have to worry about the orientation of the DSOs and deep field objects I am shooting. I can always just reorient the image if I want to in developing. But the angle of the object relative to the sensor becomes much more important when using a rectangular sensor. So, if using a rectangular sensor, you will have to anticipate having to rotate your camera from time to best fit everything onto the sensor. And this means, in addition to the camera, you're going to need a manual or electronic rotator. And that's going to add millimeters to centimeters to your image train, possibly driving your back focus position off, making it difficult to impossible to focus. If nothing else, it'll complicate the image train. For myself, I figure astrophotography is complicated enough, and I'm a big fan of keep it simple, stupid, so I'll leave the rotator out of my image train and stick with my square sensor. But format really is a matter of personal choice. However, something to consider with format is sensor size. I know for a fact there are some, I don't know how many, but there are some, I would say plenty of persons in astrophotography, and certainly a lot of persons in regular photography that feel bigger is better. The bigger the sensor format, the better. In terms of regular camera sensors, one might say they feel that 2/3 of an inch is better than 1/2.5 inches, 1 inch is better than 2/3, micro 4/3 is better than 1 inch, APS-C is better than micro 4/3, and full frame is better than APS-C and everything else. I'm going to straight up tell you that is categorically wrong. For so many reasons that it really goes beyond the scope of just this one video. But, just as an example, there is a common myth in ordinary photography that bigger sensors shoot better in the dark and give better dynamic range. But that's only a half-truth. It's not the bigger sensor that gives the better dynamic range and the better dark performance. It's rather that if you have a 1-inch sensor with 20 megapixels and a full-frame sensor with 20 megapixels, the individual pixels in the full-frame camera sensor are going to be significantly larger than the pixels in the 1-inch camera sensor. Pixels are like buckets for light, and big buckets can capture more light than little buckets. So it's actually the pixel size that matters, not the sensor size that matters. Sensors with bigger pixels will be able to capture more light more effectively. Astrophotography camera makers are well aware of this, and factor pixel size in their choice of sensors when creating astrophotography cameras. Where sensor size really matters in astrophotography is in consideration of what kind of subjects you want to shoot. If you want to shoot vast and impressive nebulous complexes, like the Orion Complex or the Heart and Soul region, then you're going to want a low focal length telescope and a camera with a big sensor to capture everything in the telescope's field of view. But if your goal is to shoot fine detail within those structures, or to shoot distant deep sky objects and far more distant deep field objects, which are subjects that will easily fit into the field of view of even very small sensors, then truth be told, you're going to be better off going with a smaller sensor format. Part of the reason, plain and simple, is cost. Smaller sensors cost much less than large sensors. But the fact is, larger sensors will produce subs that eat up much more memory than small sensors. If you're shooting a distant object that only occupies a tiny portion of a large sensor, then that's a lot of wasted memory being eaten up and a lot of wasted space. That's memory that's going to take up your shooting rig's hard drive, memory that's going to take more time to transfer to your computer, memory that's going to take more time for you to stack, and memory that's going to take more time for you to develop unless you crop out the excess early. In other words, especially in context of astrophotography, getting a sensor that's too large has no real benefit and only wastes resources. So you need to have a sense of what kind of objects it is that you want to shoot when you pick out an astrophotography camera. There are applications that you can use to look at deep sky objects and observe how they will fit in your telescope's field of view with a sensor camera laid over that field of view. My favorite is stellarium. The image right now shows how a sensor at a given focal length would fit over a region of nebulosity. The next thing, megapixels. Along with sensor size, megapixels are the other trap that camera manufacturers often use to lure new photographers into buying things they don't need. New photographers tend to think bigger sensors and more megapixels are always better, and it's simply not the case. In photography, 12 megapixels is kind of a magic number, because 12 megapixels is the point at which an image viewed at typical viewing distance can no longer be told from chemical photography. Chemical photography, if you don't know, really has the ultimate resolution because the resolution goes right down to the molecular size of the photographic chemicals. Digital photography, even to this day, isn't even close to that. But our eyes don't have that kind of resolution. At 12 megapixels, our eyes can no longer tell the difference between a chemical and a digital photograph at ordinary viewing distance. In astrophotography, pixel count becomes even more important because the more pixels, the smaller they have to be. Remember a moment ago I said that pixels are like buckets for light. The bigger the bucket, the more light each pixel can capture. So if your pixels get smaller, then you could say the fine resolution of the overall image becomes more detailed, but that's not really true due to the way light works in telescopes. Or rather, it's more complicated than that, and explaining it is way beyond the scope of this video. If you want to really understand that, I did a video on this a year ago called How Does Focal Length Change What Size Pixels a Camera Sensor Needs? A link will appear in the top right for it now, and there's also a link in the description below. Basically, if you're going to shoot high focal length, you need big pixels. If you're going to shoot low focal length, you need smaller pixels. There are calculators online that will help you determine what size pixels are ideal for whatever focal length you're planning to shoot at. I've listed my favorite one below in the video description, but I will add that I have found it perfectly acceptable these days to use cameras that are a little oversampled, or in other words, that the pixel size is a little smaller than what's recommended. Modern cameras are so good, even compared to what was out just 5 years ago, that they handle this well, and I think the finer pixel size gives me a little more detail in the bargain. In the top row of the far right column, we see information on an area called ADC. ADC refers to analog to digital conversion, and this stands for the camera's ability to turn light collected by a sensor into electrical charge, and then to turn that electrical charge into numerical values that the camera can then process into an image. The 14-bit ADC of the IMX533 sensor can describe 16,383 degrees of difference in brightness between each pixel. This is because bits are binary numbers, 0 and 1, and a 14-bit number has a value between 0 and 16,383. 0 is black, 16,383 is white, and each pixel can be divided up into 16,383 shades between true black or 0 and white, which is full brightness at 16,383. And that's plenty because the human eye can only determine shading to within 9 to 10 bits of accuracy, which is just over 1,000 different levels of shading. Nonetheless, especially when shooting extremely faint objects, having higher ADC can be useful. The higher the ADC, the more information is there for development software to work with, and that's important when working with objects that have extreme faintness or extremely subtle difference in detail, because the development software can detect those differences and bring it out in such a way that it works better for the human eye. With all of that said, I found the 14ADC of the Player One Aries M to be more than adequate even for extremely faint deep field objects, though I certainly wouldn't object to 16-bit ADC if I could get it. In the second row, first column, we see the connectivity of the camera. It states it's USB. Most modern cameras are going to work with some kind of USB. USB 3.0, 3.1, 3.2, or some other derivation of USB. USB is very fast and effective. But I wouldn't spend a lot of money on really fast and effective faster USB connections either, because faster data transfer rates are subject to interference. They're just not as reliable. And many users have found that the cameras jam up and fail to save subs when using the faster USBs. So to this very day, my camera writes its subs to the mini PC attached to it with USB 2.0. It just takes a fraction of a second per sub and is more than adequate for the task. However, fast USB is pretty cheap these days, so if your camera comes with something faster, 3.0 or faster, sure, get it. It probably won't make much difference cost-wise, though you may find you have to resort to a store USB function in order for the camera to write its information correctly to your computer. The second column of the second row describes the buffer of the camera. Buffers are very important, especially when shooting extremely faint objects, particularly if you're going after deep field objects, which could be magnitude 22 or fainter. The buffer is very fast memory that the camera writes the information from the sensor to, and for several reasons, faster is better. One of those reasons is you don't want the image sitting in the sensor. You want to clear that information off the sensor, get it into your memory, so that your sensor can start shooting the next sub as fast as possible and make the best use of the night. The buffer can then write this cached information to your computer while the camera goes ahead and starts shooting the next image, allowing for uninterrupted and stable imaging and data transfer. But another thing that I think is often overlooked by persons new to buying Astro cameras is the buffer is very important in combating amp glow. While the information gathered in a sub is sitting in the sensor, it's subject to the camera's electronics, and this can produce amp glow. By moving the information as fast as possible from the sensor to the buffer, the information is made stable and no longer subject to amp glow. The third category in the second row, where it says 43 FPS, it's really a category for persons who are doing planetary photography, lunar photography, maybe solar photography. because those objects are so bright that they can shoot extremely short subframe exposure times to minimize the atmosphere's wavering effects we're seeing on the individual images. But for our purposes and consideration of cameras for deep sky and deep field imaging, we're going to skip that. It doesn't really apply to us. The last column in the second row lists the camera's delta T. This is its maximum ability to cool the temperature below the ambient temperature. And for the Aries M, it says between 35 and 40 C. This means that the camera can cool itself to between 35 and 40 C below whatever the ambient temperature is. If the ambient temperature outside was 10 Celsius, then I could theoretically cool my camera down to minus 25 to 30. In reality, and based on some very good research, I never cool my camera lower than minus 5. The harder you're trying to cool your camera, the harder it has to work, which means its cooling system will last less long. And for my camera and the ambient temperatures of a Canadian night, I find minus 5 Celsius gives consistently superb results without overstressing the camera hardware. Now we're into the bottom row, first column, no amp glow, and this is huge. Old cameras had amp glow. Amp glow appears as a pattern of light to one side or another wherever the sensor hooked up to the camera's electronics. Old cameras, and again by old cameras I mean cameras that were standard even just 5 years ago, required dark frames to counter this. Dark frames were a type of calibration frame made specifically to counter the amp glow. Unfortunately, shooting dark calibration frames was an imperfect solution. If you ever go digging around an astrophotography forum like Cloudy Nights, you're going to find that many owners of those old cameras report that dark frames didn't work perfectly. Sometimes it made a wonderful difference, sometimes not so wonderful. And often images were left with faint traces of amp glow scarring them. But this is an old problem. Due to things like increased buffer speed and improved electronic design, amp glow is pretty much a thing of the past. Both my current Astro cameras have Sony 5XX generation sensors. These are well into the post-amp glow era. And I can tell you, I have literally never bothered to shoot dark frames for either of those camera sensors. It simply isn't necessary. If you're willing to tolerate amp glow and shooting dark frames and the risk that you might not be able to get the amp glow scar out of your image, then you might try saving some money by getting an older camera sensor, but personally I wouldn't recommend it. I've just read too many reports from people of scars of amp glow that they just couldn't remove no matter how good the dark frames. And I believe that when shooting extremely faint deep sky objects or deep field objects which are inherently super faint, any trace of amp glow will stand to significantly impact the image. The second column on the third row refers to well depth. Well depth is one of the most important characteristics that you can look for in a camera. Think of each pixel as a well, or better, a cup, and electrons as marbles. Well depth refers to how many marbles it takes to fill up the cup. If the cup is empty, it appears as black. If the cup is full, it appears as white. Now you don't want your pixels to really ever turn white, because when they're white, they're blown out. This means that they can't get any brighter and any white pixels around them will all look the same. So there's no detail, there's no definition in the image where all the pixels are white. That's what a blown out area is. Here's an example. If a camera has a deep well depth, it will take a lot more electrons to go from full black to white. This means the camera can inherently shoot higher dynamic range objects. So, it can capture an object's very bright areas along with its fainter areas without blowing out the very bright areas, as with this example of the Great Orion Nebula. And cameras with a deep well depth will also give you better stars, because stars are typically much brighter than whatever object it is that you're trying to shoot, and cameras with full well depth are unlikely to blow out the stars, because the stars simply won't be able to fill up the cups with electrons. And because pixels with larger full wells can hold more electrons, and the number of electrons held by a pixel precisely shows how bright it will appear, sensors with larger full wells will present better dynamic range, which is the difference between bright and dark areas. And this ability to show very subtle differences between zero full well or pitch black and the faintest trace of signal, which is what we're often working with extreme deep field objects, is especially important in deep field imaging. Deep field objects that are often halfway or more across the observable universe, are frequently magnitude 22 or fainter, and being able to distinguish them from the darkness of space requires a camera that is capable of revealing the subtlest signal of light within that space. Even more important is the next stat, quantum efficiency. Notice here that the monochrome version of the Player One Aries M camera has a quantum efficiency of 91%. Now, quantum efficiency varies over frequency. I don't want to make this too complicated, so for the moment, we're just going to go with that number of 91% and talk about what it means. Quantum efficiency really is very simple to understand. Photons come to us from objects far off in space, and to turn up in a photograph, they have to land on your camera sensor's individual pixels. However, those pixels are imperfect machines, and for various reasons that are beyond the scope of this video, they don't record every photon that lands on them. A quantum efficiency of 91% simply means that out of every 100 photons that reaches any camera pixel, 91% are detected and recorded as information. The other 9% are wasted. Now, I know somebody's going to step in here and say, well, you're not accounting for the photons that are absorbed by the atmosphere and the photons that are absorbed by the optics of the telescope, but that's because that's also beyond the scope of this video. We're just talking about picking good cameras here. And whatever is going on in the atmosphere, whatever is going on in the telescope, those are kind of fixed variables that we just have to live with. Ultimately, what we as astrophotographers have to work with is whatever finally makes it to the camera sensor. And to make the best use of that information, we want to pick out the camera that's going to detect the best. And to be very frank, the quantum efficiency, I think, is the single most important characteristic of any astrophotography camera, because this indicates how effective your camera is going to be at picking up that light over time. Just a few years ago, just 5 years or so ago, the average quantum efficiency of many astrophotography cameras was around 50%. This meant it would have taken one of those cameras 1.82 hours to pick up as much signal as a modern camera with a quantum efficiency of 91% can pick up in 1 hour. Except, those old cameras also had much poorer well depth, like the old ZWO ASI 1600, which had a well depth of 20 KE, as opposed to a modern camera's well depth of easily over 70 KE. So with the limitations of older cameras, would the signal of extremely faint deep field objects even have shown up? Maybe with enough time, but I'm not entirely sure. If somebody out there has shot deep field objects with those old cameras and actually knows, I'd love to hear. Please share it in the comments section below. But the fundamental thing to remember is you're going to get much faster performance if your quantum efficiency is high, and you're going to get a much better range of information if your full well depth is high. And a camera with a better buffer memory and no amp glow will give a cleaner image. The last column of the last row covers read noise, and while it's listed last, it is also one of the most important characteristics. The read noise of modern cameras is extremely low. Notice it notes the read noise here at 1E, or 1 electron of read noise. Read noise is the random electronic noise added to an image when the sensor reads out data. It's just noise generated by the circuitry of the electronics. It's going to be present in all your images, no matter what. With modern cooled cameras, read noise is so low that for many objects, especially the objects of moderate brightness or brighter, it's barely relevant at all. If your targets are fairly bright nebulae, like the Heart and Soul Nebulae like I mentioned earlier, the Great Orion Nebula, the Pleiades, or any of the other moderately bright to bright objects in the sky, honestly, it's going to be virtually irrelevant. Where it will become really relevant is when shooting extremely faint DSOs, and especially when going for those ultra-faint deep field objects. Especially with deep field objects, you're going for galaxies that can barely be seen at all. Remember, are more than 1.5 million times fainter than the human eye can see. The faintest, wispiest traces of light, so faint that one might say that it's a miracle a photon from an object 20+ billion light years away could ever happen to fall into one of our camera's pixels at all. And our camera has to be able to pick up that extremely faint, weak signal against the background of its own electronic noise. Allow me to use a simple illustration to show how challenging this is. Imagine a friend is standing about 2 arms lengths away from you, whispering to you. The whisper is faint, quiet, but you can still hear it. Now, imagine there is a road behind you and cars are traveling up and down it. Technically, you can still hear your friend, as in the energy of the sound is still reaching your ears, but you can't discern the words because of the noise of the road. But you and the friend stand right there near the road for hours and hours while your friend continues to whisper. Eventually the sun goes down, the night gets later and later, and somewhere in the wee hours, during the deep AM hours, the traffic subsides entirely. All but for the occasional car that goes by every few minutes. And now, once again, you can understand what your friend is saying. Technically, you could always hear him, but when traffic was going by, whatever he was saying, the signal was drowned out by the noise of the traffic. But when the noise finally went away, you could pick out the words that he was saying to you just fine. Well, imaging extremely faint DSOs and deep field objects against the background of a camera's noise is very much like that. The faint whispers of signal coming from objects on the other side of the cosmos can only be discerned if the noise from the camera's own circuitry does not drown them out. Fortunately, extremely low read noise is pretty standard with cooled modern CMOS cameras. And it's not hard to find modern astrophotography cameras with read noise of just 1E. Never be tempted to save money and get a camera with a higher read noise. Because if your goal is to image extremely faint DSOs and deep field objects, the read noise will very effectively drown out the whisper of those extremely faint signals. The last thing I'll add is that for shooting extremely faint DSOs and deep field objects, cooling is very important. Heat, whether from the camera's own electronics or the ambient environment, can generate electrons within the silicon of a camera sensor. Because astrophotographers, like astronomers and like scientists in my own field, love to give confusing and unobvious names to everything, these electrons are called dark current. But what matters is not remembering the jargon. What matters is that understanding that for every 6 degrees Celsius the temperature is lowered, that kind of noise is reduced by half. And when trying to go after extremely faint objects, the key thing is to reduce noise in all its forms so that the background signal can stand out against the backdrop. And with extremely faint objects that really matters. They are so faint, they are like mere whispers, easily drowned out in any amount of noise. So, the more noise removed, the more clearly the signal comes through. Meaning, if your goal is to shoot the faintest deep sky objects and pursue the faintest deep field imagery, a cooled camera really is necessary. So, in summary, don't get caught up in the megapixel trap. Bigger pixels are more important than lots of pixels, especially in astrophotography. As an example of this reality, just pop over to the Sky Story Astrobin and take a look at those images, noting that all of them were shot with only 9 megapixel cameras. Well, actually the earlier images from about 2.5 to 3.5 years ago were just shot with the Uranus C, which is only 8.3 megapixels. And don't get caught up in the sensor size mania that infects so much photography of all kinds. Bigger sensors are not necessarily better, and sometimes they work against you. Not only do they cost a heck of a lot more, but they can lead to a lot of wasted memory, a lot of extra stacking time, and a lot of extra development effort. If you're struggling to determine what size sensor you actually need, think about how the kind of objects that you want to shoot are going to appear within the field of view of your telescope. Stellarium, which is a free planetarium application used by many astrophotographers to plan their shooting, will actually allow you to enter the specs of your telescope and the specs of your camera, and show you how the objects that you want to shoot will fit in the camera's field of view. The factors that really matter for shooting the faintest objects are the ADC, get 14 bits or larger if you can, your buffer, get the fastest, largest buffer possible. Make sure that your sensor is a non-amp close sensor, though most modern sensors are. Get the deepest full well depth possible. Get the highest quantum efficiency possible, and frankly, in terms of mono cameras, I wouldn't accept a mono camera with a QE lower than 90%. For color cameras, I wouldn't accept a color camera with a QE lower than 80%. And get a camera with the lowest read noise possible. These days, I would not honestly accept a camera with read noise higher than 1E. I hope that helps in your camera selection, though I'm sure some of you have many questions because extremely deep topics such as camera selection can go down infinite rabbit holes of complexity. And the reality is we could easily take an entire video to discuss any one of these particular traits. But I wanted to keep this video as simple and straightforward as possible for those new to astrophotography and just trying to figure out what camera should they get if their goal is to shoot very faint DSOs and deep field objects. Have a great day. If you have any thoughts, observations, or questions, please leave them in the comments section below. Now, as always, get out there and shoot the sky.